It's a lot of fun to see many old friends, and there are a lot of memories that many of us, the older people, have about how things were from the time that the Rutgers group moved into those trailers in '89 until all this today. And I guess the other thing that's very noticeable is the great young people that are continuing this tradition. So I'm very happy to be here. I guess according to Spires, I wrote 11 papers with Nati, and many people here commented on how he influenced their life and research, and I don't want to repeat this, but I basically agree with everything everybody said. The one thing that I think he probably only told me is basically every time I see him, he tells me that he taught me everything I know about interacting with graduate students. And so for what it's worth, I guess it's another contribution he made for science or whatever. What I want to do today is talk about n equal 1, d equal 4 supersymmetric dynamics, and this is a subject that to a large extent is associated with Nati from his work with the previous speaker and Michael Dine in the 1980s until his full elucidation of the phase structure of n equal 1 SQCD in '94, which is, I guess, already 22 years ago. But what I want to do here today is not so much talk about the past, but rather discuss how Nati's results and some subsequent work led to new questions that actually remain open. And what I'd like to use the rest of this talk for is explaining this last statement that there is there are reasons to believe that there are qualitatively new phenomena in n equal 1, d equal 4 theories that remain to be uncovered. So not some details about this dimension or that dimension, but qualitative things. And that there are new techniques that we will need to do that. Now, however, in order to kind of set all the notation and stuff, I'll have to start with the old things. And so let me very briefly remind you, I don't think in this audience I need to do a lot of work on this, so I'll just flash through some old facts. So we'll be dealing with, at first, with SU and C gauge theory with NF flavors. And the picture, according to Nati and his collaborators in this theory, is a certain structure, which I'm not talking about in detail here, but just pictorially, that as you vary the number of colors and flavors, and in particular this discrete parameter, the ratio of the two, which will play an important role in this talk, the behavior of the theory changes in a way that is controlled. So, of course, we know from the early 70s that for sufficiently large number of flavors, the theory is not asymptotically free. So that's this region over here. And we also know from slightly later times that as you pass the asymptotic freedom bound, at first, weak coupling techniques are applicable. This was pointed out by various people, in particular Banks and Zaks, in the non-supersymmetric case. But in the supersymmetric case, there is an extra element which is worth mentioning here for future reference. And that is that when the whole RG flow from the UV to the IR remains in the weak coupling region, the infrared U1R current that becomes a part of the superconformal multiplet must be preserved throughout the RG flow. So this makes things much better in the supersymmetric case than in the bosonic one, because you can look in some open neighborhood of this asymptotic freedom bound and identify this U1R current, and in particular do things like calculate scaling dimensions of various operators, central charges, and such. Now, as you continue to move to the right in this diagram, the RG flows, of course, become longer, And eventually, all sorts of more exotic things can start happening. For example, the U1R current that you, as I said, could identify when the coupling is sufficiently weak, when this X is sufficiently small, can start mixing with other currents that do not exist in the UV and are sort of accidental symmetries that only appear in the infrared. And one famous example of this is the decoupling of gauge invariant chiral operators whose dimension naively dips below the below the unitarity bound. And this is something that's easy to take into account, but I will not discuss it here. If you look at, say, the SQCD example that Nati and his friends analyzed, it's easy to see that it cannot be that that's the only thing that you need to do in order to analyze the strong coupling region. So if the only thing that you needed to do was to take into account this effect, then the picture would be much less rich than this. In fact, what happens is that if you assume that there's nothing more exotic than that happening, you discover that there are violations of the A theorem at sufficiently large values of the coupling. And so something more dramatic has to happen in SQCD. And that something is Seiberg duality. So again, for this audience here, I don't need to talk much about what Seiberg duality is. There's some other gauge group, similar charged matter, some singlets, and the superpotential. And the important thing about this duality is that the coupling X that I talked about before is related in the dual theory to the coupling in the original theory by a relation like this. In other words, as the original coupling grows, the dual one decreases. And so the picture in the end is here the following. So as you move to the right, the original theory becomes more strongly coupled. The magnetic one becomes more weakly coupled. This region, in some sense, is a region in which there's an overlap of both descriptions. And if you move out of this region, either to the left or to the right, one of the descriptions breaks down. To the right, the electric description breaks down, and to the left, it's the magnetic one. So the Seiberg duality really, its role in SQCD is to answer this question: what is the more exotic effect that happens as you go to strong coupling, more exotic than just decoupling of these free fields? And that these violations of the A theorem that I referred to, which occur if you don't take this into account, are due to this breakdown that I just mentioned. All right, so that's the SQCD story. And you can ask what happens if you generalize it in various directions. Well, I mean, of course, it could have been that if you generalize it, all that differs between other examples, and this is details. And by generalize, you might mean, say, different gauge groups and other matter content, superpotentials, etc. Say, in string theory, people talk a lot about quiver theories. But what we will see sort of a little later in this talk is that if you just keep the gauge group the same and add a little bit of matter, there are some big changes in what the dynamics can do. And so it's actually striking how little you have to move away from the original examples to get theories in which this kind of picture that I just outlined must break down. So, well, what can we do? So if we want to keep the gauge group the same, we might want to add some additional matter fields. So for example, we can add matter in the adjoint representation. And so I'll review very briefly what happens when we add one adjoint chiral superfield and then focus on the case I'm really interested in, which has two of them. So this is something that was looked at carefully by Ken Triligator and Brian Wecht, and as well as myself and some people. And the picture that arises there is basically the following. If the superpotential vanishes for this adjoint and the fundamental fields, then you have to use A maximization, which of course took until 2003 to appear. But once you know about A maximization, you can solve this theory. And it basically has a non-trivial infrared fixed point whenever it's asymptotically free. There is nothing more exotic, it's believed, in this theory than just decoupling of free fields. And the infrared, the U1R current, is something that you can see essentially in the UV. Now you can ask, how do we know this? And basically the honest answer is that there are no contradictions in the resulting picture. It could be that it's not true, but there is no signs of that here. And by the way, this theory also doesn't have any kind of analog of Seiberg duality, but in the picture I presented, it's not an accident. It's simply due to the fact that there's no need for it. The reach of the UV description of the original theory extends all the way to small nf or large x. You can try to turn on superpotential. So if you want to preserve the SUNF cross SUNF chiral symmetry associated with the fundamentals and you want renormalizable theories, the only thing you really can do is a cubic superpotential. And in that case, you get some structure which is similar to the SQCD story. There is a weak coupling regime where Banks-Zaks type analysis is valid. Then there is a point at which the theory exhibits runaway behavior. And in between, it moves from a weak coupling to a strong coupling regime, where towards the top of that range in X, the better description is in terms of some dual theory, which has more meson fields, more singlets, etc. The one thing I want to stress that's important here is that the fact that this whole structure makes sense is importantly related to the fact that the F term of this X field is imposing the constraint that the square of the adjoint field is 0, which truncates the chiral ring in a way that does not, is not sensitive to the rank of the gauge group. And that's why it makes sense for theories with different gauge groups to have the same, say, spectrum of chiral operators. So that basically works like in SQCD. And in fact, you can generalize it to higher polynomial superpotentials. Here, there is a kind of a new feature that appears, which is that naively such superpotentials should not play a role in the infrared because they're irrelevant, but one can show, again, using things like A maximization, that if the gauge interactions are strong enough, they become relevant and lead to non-trivial fixed points. In fact, here, again, the fixed point associated with this thing only exists when the coupling is below a certain value, and then you develop some runaway behavior as well. And again, an important element in this picture is that the F term of the superpotential imposes this constraint that knows about K, but does not know about the number of colors. And the duality in all these cases is a strong weak coupling one. So the upshot of all of this is the following, that if you go from SQCD to the theory with one adjoint chiral superfield in addition to the fundamentals, this problem is basically understood. However, you know, in the process of understanding it, we did learn a few things. For example, I actually don't know whether when Ken and Brian developed A maximization, this example motivated them, but it's clear when you look at this example that you need something like that to understand the theory even at weak coupling. And there is this fact that highly irrelevant operators play a role in the IR. But okay, so we understand all of this and things work nicely. So that's all in the past. Now, the question is there any benefit to adding more adjoints? So if you add 3 or more, then there's nothing interesting to do here because you get free field theories in the IR. And so the remaining case to analyze is the one where there are 2 of these adjoint superfields. And as I'll discuss for the rest of the time, this case has some pretty serious difficulties associated with it. So at first, when you start looking at it, everything looks okay. So you have 2 adjoints that I will denote by x and y. You have these fundamentals. And these people analyzed this problem in detail, and what they found is that if the superpotential vanishes, you get basically the same kind of structure as for one adjoint. In other words, a non-trivial fixed point. If you assume that the structure you inherited from the UV is valid all the way to the IR, you do not run into any trouble. There is no analog of Seiberg duality to describe the strong coupling limit because you don't need one, and everything looks good. The same is true for the case where you take one of these adjoints and turn on a renormalizable superpotential for it. However, this is sort of where the good news ends. And when you ask, OK, what else can I do? Well, if I want to be renormalizable, then the one remaining thing you need to look at is what happens when you add a cubic superpotential, say a cubic both for x and for y. So if you just try to follow your nose, you get all sorts of puzzles very quickly. One thing that you immediately notice is that the F-term equations for these x and y, because these are NC by NC matrices, do not actually restrict the chiral ring that much. For example, the analog of the meson operators are basically any string of x's and y's where no 2 of them are adjacent, sandwiched between a q tilde and a q. Similarly, you can write operators like this just for the adjoints. And so that already tells you that something fishy is going on because, it's hard to see how this kind of spectrum is going to be reproduced by any gauge theory with a different gauge group. So the next thing you think is, well, OK, maybe it's like these W equals 0 examples, like these cases, where everything is OK, the ring is not truncated, but there's no problem. Well, it's not, that doesn't work either for the following reason. So if you try to go in this direction, you would say there is a unique U1R, which assigns, it turns out, these kinds of charges to the fields. And you can try to use it to do physics. And what you find immediately is an inconsistency with the A theorem. So there are various ways to see this. One nice one that appeared in a recent paper by Ken Intriligator and Emily Nardoni is to note that this system has a flat direction. So these equations, x squared equals 0 and y squared equals 0 equals 0, have a solution in which you take x to be the Pauli matrix sigma plus, let's say times as an identity matrix, and y the Pauli matrix sigma minus. And for any values of this complex parameter b, you get a solution of the f and d term equations. Now, so this is basically a flat direction, which takes you from the original theory in the UV to a theory with a smaller gauge group, some number of flavors, and a single adjoint field with no superpotential. However, when they calculated the difference of the UV and IR central charges, they got this kind of picture. So clearly something is going wrong when this coupling is around 4. And so it's not going to work. Like something needs to happen before you get to this point because otherwise you believe in violations of the A theorem. Now, so what can we say about this? In all the previous examples, that I mentioned, when such a phenomenon occurred, you were saved by Seiberg duality, in the sense that the description that you were using to produce pictures like this broke down, and you needed to use some different variables, and you could not see from the original description this behavior. However, this was in these examples where, as I mentioned, the chiral ring was truncated in a way that this is not. So this is a problem for those descriptions. And so you are in this odd situation that this example that is a very small modification from the original N=1 SQCD studied in the early 90s, has some elements of each of these two classes of theories. It seems to require something like Seiberg duality to avoid violations of unitarity. But on the other hand, the chiral ring is sensitive to the rank of the gauge group. And so it's not clear what that should be. So on some level, this is sort of one point where one can stop. So at this point already, you know, the bottom line of this discussion is that something is different here. You know, like the techniques that you're used to using don't work, and so something additional needs to happen here that we have not seen before. That sort of saves unitarity here. Now, remarkably enough, this situation is one where there is both a proposed solution and the proof that this proposed solution cannot work. So this actually, it's sort of reminiscent of some review by Joe Pulczynski on the C theorem, where he said that in 2 dimensions there's both a proof and a counterexample. So this is like that. So this proposed solution was actually proposed before a lot of this stuff was even realized. And it was proposed by John Brody, who was a student here. And he said that if you look at a much more general class of superpotentials, of which this one that I just discussed is an example, the k=2 example, he argued that this class of solutions, so he noted that if this level k is an odd integer, then things work out nicely, because this y, which is not exactly the same as the y I had before, they're related by some transformation like this. This y, you can show, satisfies some constraint in the classical chiral ring that its cube is 0. That truncates the chiral ring to a set of 3k mesons, and there's some analogous statement for other things. And correspondingly, the dual gauge group is SU3k and F minus NC. So for odd k, he noted that there's some story that works. And we need it for even k, in particular k=2, but there this constraint is absent, at least classically. The ring is not truncated, and the duality seems suspect. So people that looked at this problem over the years, like I guess including Matt Strassler here, there were fluctuating opinions about this, whether it means that for even k this whole story is not true, but on the other hand, you know, you can flow from a superpotential like this with odd k to one with a lower even k. But on the third hand, in the recent Intriligator-Nardoni paper, they showed that there are some issues with this flow. So it was never very clear what's going on. The one thing that is true for sure is that there's something that needs to happen here. The structure, as I presented it, just is inconsistent unless you believe that the A theorem can be violated at strong coupling, which we don't. Okay, so let's see, I have 10 minutes or so? A little more. Okay, so what I want to do, so I'm not going to solve this problem here, but I will propose an approach of thinking about it that might be useful. And the approach is the following. So suppose you take this superpotential that we were interested in, and you say, I'm interested in imposing this condition y cubed equals 0 that Brody found necessary for his work. So one way to do this by hand is to add an additional coupling that looks like this. And when you do that, the F terms of Q and Q tilde give constraints of the sort that are needed for this Brody duality. So if you turn on this coupling, in its presence, you can make the argument that this duality that we need for things to work out is more reasonable. Now, this coupling does there are a few things to say about it. One is that, of course, it breaks the chiral SUNF left cross SUNF right symmetry. So eventually, we will be interested in we're interested in what happens when it's not there. But let's put it in for now. A little bit like when you study spontaneous breaking of, like magnetization, you turn on a magnetic field and then you want to remove it at the end. So let's put it in. The other thing is that the R charge of this coupling is given by this formula. So it has this interesting property that when the coupling X is larger than the self-dual value, if you believe in Brody duality, then this is a relevant coupling. And when it's smaller, then it's an irrelevant coupling. If it's exactly at the self-dual point, there is a moduli space, like a conformal manifold associated with it, which we'll say a few more things about in a second. At any rate, if you turn this thing on, it seems like there is possibly a less exotic story. But there are all sorts of confusions that I don't have time to list. So because of that, let me quickly review what happens when you do the exact analog of adding this term in the examples that we do understand, which are the A-type superpotentials for one adjoint and this thing for odd k. So let's start with the single adjoint that I discussed before. Well, the F-term condition that we're interested in is just x to the k equals 0. And so the term that's analogous to the one that I'm proposing adding here, in this case, looks like this. Now, superficially, you might think that this coupling is just nothing because, before you add it, x to the k is 0. So this guy is not a chiral operator. So it's like, it's a D term, basically. So adding it to the superpotential is stupid. But in fact, it's not true. The quickest way to see that it's not true is to take this superpotential and shift the X field by some multiple of QQ tilde, where here QQ tilde for me is an adjoint and summed over flavors. And what you get when you do this is that this shift eliminates the lambda term, which is something that is guaranteed to be possible just because Q tilde x to the kq is not in the chiral ring. But it generates higher order terms. In particular, it generates a quadratic term in the mesons and then some higher order terms that I don't need to worry about for now. So these MJs are just the usual mesons. Now, so what is the physics of this guy? Well, again, if you look at the R charge of this object, it has the property that if you are above the self-dual point in terms of this AK duality, then it's relevant. And if you're below the self-dual point, it's irrelevant. If you're at the self-dual point, x equals k over 2, it's a truly marginal operator. It generates a part of the conformal manifold. So what do you want to do with this? Well, so one question is, so when it's irrelevant, when the coupling is small enough, then you know what it does in the infrared, namely nothing. The coupling just goes to 0. Question is, if the coupling is above the self-dual value, then it's a relevant operator. It's equivalent to this relevant operator, and you can ask, what does it do? Now, you can answer this question in the electric variables or in the magnetic ones, because there we have the duality. And basically, you just take this thing, you write it in the magnetic theory, where these are just singlets. These are quadratic terms in the singlets. You can integrate the singlets out, and you get a quartic plus higher order term interactions in the magnetic quarks. But now this is an irrelevant perturbation. So in other words, when you turn on this coupling in the electric theory, and the coupling is such that the lambda thing is relevant, then the theory flows in the infrared to the magnetic theory without any singlet mesons and vanishing superpotential. So this is an RG flow from the electric theory to the magnetic one. And for exactly the self-dual point, there's some conformal manifold where duality implies a relation between small lambda and large lambda. So that's what happens in this case. And something similar happens in the decay case with odd k. So there's some slightly more involved analysis that I will not go into. Basically, if you take, where was it? You take this superpotential, and k is an odd number, then you know ahead of time, because of this result that I mentioned, that y cubed is 0 in the chiral ring, you know you should be able to get rid of this term by some shift of variables of the sort I did before. And so that's the shift in question. And you find, just by explicit calculation, that the coupling that I'm interested in is again equivalent to some bilinear coupling in the mesons or quartic coupling in the quarks. So again, it's the same story. If you're below the self-dual point, the perturbation turns off in the infrared. And if you're above the self-dual point, the theory just flows to the magnetic theory with no magnetic mesons and superpotential. So these are all cases that are understood because of the existence of these dualities. And so now we can go back to the reason we started this whole game. So the question is now, if we take the theory that we do not understand, the decay theory with even k, and we turn on this coupling, what physics is associated with it? So some of the elements of the discussion are the same, like the calculation of this R charge doesn't care about whether k is even or odd. And so, for example, if the coupling x is above the self-dual value, this is a relevant perturbation, and you have to be able to answer the question, where does the theory go? Now, at the same time, as I mentioned before, it's reasonable in this case to expect that Brody's duality provides a good guide to the physics simply because the constraints that he used are valid. And so we can conjecture, and this is not something that I have proof of, that in this case, like in the other two cases that I just outlined, the infrared behavior at x above this value, or the large lambda behavior at the self-dual point, is the magnetic Brody theory with the singlet mesons integrated out. Now, so this is not something I'm 100% sure of, but let's assume for a second that that's true. What does that mean? Well, so what it means is that in the electric variables, as I said, the whole rationale of adding this thing in was that it imposes these constraints and therefore cuts off the chiral ring. But now we are saying here that where is it? So we're saying here that when we turn this coupling on and flow to the IR, we get a theory which is just pure, pure decay gauge theory with these adjoints and that superpotential, in which seemingly the constraints that Brody assumed on the superpotential are not valid. Now, if you believe in this flow, one of two things must happen. Either the magnetic theory, despite appearances, must also satisfy these constraints. In other words, the pure decay theory without any additions must satisfy these constraints, or that the electric variables break down right there. So the picture that this leads to is the following, that if you look at these theories and you take k to be an even number, then there is a region around the self-dual point that we kind of started from, in which quantum mechanically this constraint is valid. And then outside this region, it's absent. Sorry, this is a typo. Outside of this region, it's absent. So, for example, what that would mean is that in the original theory that I started from, this theory here, naively you would say that the only interesting point in the coupling space from the electric point of view is the point at which you lose asymptotic freedom. In other words, I guess x equals 1, little x equals 1. But it seems that these considerations suggest that there is a larger value of the coupling below which the sort of naive analysis that you would do here, which has a chiral ring that is not cut off, that has this kind of chiral ring, that picture is valid. But then when you pass some critical point, which in coupling is below the self-dual point, it changes to this other sort of collapsed chiral ring. So this constraint is satisfied in some region, in that case k equal to 2, around the self-dual point, which is x equals 3. And I want to stress that this is different from, so there are two different things that you might mean by saying that some constraint on the chiral ring is absent classically, but appears quantum mechanically. One is that, it appears quantum mechanically for arbitrarily weak coupling, and the other is that it only exists when the coupling is sufficiently large. So what I'm saying that happens in this theory is the latter, not the former. Now, this, I guess I don't have time to talk about some of the problems I mentioned with the even k theories that this helps resolve. It might help with some other problems that I didn't mention, but I don't want to, don't have time to talk about this here. And I want to stress that this is a scenario. This scenario might be true or not. If it's true, then there is an important problem here, which is to understand what's the mechanism that for some large enough value of the coupling imposes this constraint, and where exactly is this mechanism active in coupling space. But if it's not valid, then you're still left with this very serious problem that requires some other solution. And I think at the moment, this is the best one can do. So I know Ofer said that Nati doesn't like people talking about things that they're not sure of, but I'm not publishing this. And, I think it is an important problem. So here are the conclusions of this talk. I would say the most important conclusion is that it's clear that the infrared behavior of this class of theories that we know a lot about today is not really a finished problem, even qualitatively. And I think there are some dynamical mechanisms that we still haven't understood there. And one of the reasons I'm talking about this here is that hopefully in the next 60 years, Nati will find some time to work on this as well, among the other things. So let me join everyone else, wishing you a happy birthday, and stop here.
need to understand why you think it's so clear that there must be a dual description. Maybe there isn't one.
I didn't say that there must be a dual description. So here is the thing that I'm 100% sure of, okay? Well, I mean, I don't have a picture for this case, but suppose I drew an analog of this kind of picture for that theory with the two adjoint and the cubic superpotential for both fields. So the analog of this would be 1, and then there would be some region over here to the right of x equals 1, in which you understand basically what's going on from the kind of considerations I mentioned. You don't even need to do a maximization. You know what the U1R is, and etc. So now you proceed towards a larger coupling, and now you ask, well, I mean, I don't care if there is a dual description or there isn't a dual description. I just want to know, for example, what is the A and C central charge of the infrared fixed point, okay? Now, the only two things that we know how to do at the moment are, one, to take that original U1R that you inherited from the UV, and every time some gauge invariant operator goes below the unitarity bound, you correct for that. And two is, if there is a dual description, to incorporate its predictions, okay? Now, let's say you're right, that there isn't a dual description. Well, then we know for sure that everything we know how to do fails. This was, for example, the point of this graph that I copied from Ken's paper. Okay, so when the coupling goes beyond a certain point, everything we know how to do fails. Now, so suppose there isn't a dual description. I just want to know how this graph really looks. Not, let's say I don't even care about what tools you use to get there. Now, the reason I even mentioned the word dual description is that there are some additional examples that I outlined there. And in those examples, it was this kind of problem was solved by a dual description. So you could be perfectly right that here it's solved by some other mechanism. And that was exactly my point, that there is some new mechanism which I proposed one example of such, and it could be that there's something else. But there has to be something. I mean, surely this graph doesn't look like this in the end.
Any other questions? Okay, if not, let's thank David again.